Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to be looking at positive definite and semi-definite matrices. And we'll also be looking at maximum eigenvalues. So in this topic we will define positive definite and positive semi-definite matrices. We'll make an observation about maximum eigenvalues in many engineering problems, and we will look at the power method for finding the maximum eigenvalue and a corresponding eigenvector of a positive semi-definite matrix. Now, first recall that all the eigenvalues of a self-adjoint linear operator are real. Therefore, specifically, all the eigenvalues of a symmetric real matrix are also, therefore, real. Now, in many cases in engineering, it can also be guaranteed that the eigenvalues of a symmetric matrix are additionally non-negative. So we'll introduce a few additional definitions. A self-adjoint linear operator that has all positive eigenvalues is described as being positive definite. A self-adjoint linear operator that has all non-negative, so either positive or possibly zero eigenvalues, is described as being positive semi-definite. Now, a positive definite matrix, therefore, must be invertible, as it cannot have a zero eigenvalue, whereas a positive semi-definite matrix, if it does indeed have a zero eigenvalue, then it would not be invertible. So, ignoring multiplicity, let's assume that we sort all of the eigenvalues from the largest to the smallest. So lambda 1 is going to be the largest eigenvalue of our positive definite or positive semi-definite matrix. And lambda min will be the smallest. The number of different eigenvalues may not be equal to the size of the matrix, as some of the eigenvalues may be repeated. But nevertheless, lambda sub min is going to be either greater than or equal to 0. Just to reiterate, if all the eigenvalues of a matrix are positive, then it follows the matrix must be invertible. A matrix is non-invertible or singular if and only if 0 is an eigenvalue of that matrix. All right, now many systems in engineering are positive definite by their very nature. Some systems are not only positive definite or positive semi-definite, but in addition, the largest eigenvalue in some cases tends to be much larger than all other eigenvalues. So that is, lambda 1 will generally be significantly larger than the next largest eigenvalue, which is greater than the next largest eigenvalue, and so on and so forth. So therefore, such a system would have a dominant eigenvalue. So, as an example, suppose that A is any real matrix. In that case, both A times A transpose and A transpose times A must both be positive semi-definite. First of all, they are symmetric, for the transpose of A times A transpose is just the transpose of the operands in reverse order. However, the transpose of the transpose is the matrix itself. So we see that the matrix is symmetric. It works the same with the other matrix, A transpose times A, all transposed. Reverse the order, transpose each of the operands, and again, the transpose of the transpose is the matrix itself. Now, we also have that all the eigenvalues of a symmetric matrix are real. Let's now show that, in this case, they must also be positive. So suppose that A transpose times A has an eigenvalue lambda. So therefore there is an eigenvector u such that A transpose times A times u is equal to lambda times u. Well, in that case, if we take the inner product of u and A transpose times A times u, then that's just u times lambda times u. Of course, that lambda can come out, and so therefore we have lambda times a value that is greater than or equal to 0. However, at the same time, the inner product of u and A transpose times A times u can be rewritten by bringing the A transpose to the other side, and that's just the inner product of A times u with itself. Well, that is the 2 norm of A times u, and that must also be greater than or equal to 0. So if lambda times the 2 norm of u squared equals the 2 norm of A times u all squared, that means that lambda, and because the 2 norm is greater than or equal to 0, therefore lambda must also be greater than or equal to 0. That is, the eigenvalue cannot be negative. Additionally, if A is invertible, then both A times A transpose and A transpose times A must be positive definite, for 0 cannot be an eigenvalue. Of course, this only applies if A is square. The nice thing is you can also do this with complex matrices, but you must instead use the conjugate transpose. All right, suppose we do have a positive semi-definite matrix, and we'd like to find the largest eigenvalue, assuming, of course, that the largest eigenvalue is significantly larger than the second largest. What we're going to do is a little bit interesting. We're going to start with a randomly generated normalized vector v0 cap. Now, because A is positive semi-definite, it is self-adjoint. So therefore there must be an orthonormal basis for r to the n, or c to the n if we're dealing with complex matrices. Consequently, this vector v0 cap must be able to be written as a linear combination of these basis vectors, each of which is an eigenvector. All right, now, if v0 cap is chosen randomly, then the likelihood of the coefficient of the eigenvector u1 cap being 0 is essentially 0. It's almost certain that the coefficient alpha 1 is going to be a non-zero value. And that's important, and that's why we choose a random vector. All right, now if we multiply this v0 cap by the matrix A, well, because v0 cap is a linear combination of the basis eigenvectors, then A applied to v0 cap is just A applied to this linear combination. However, because a matrix is linear, a matrix applied to a linear combination of vectors is equal to that same linear combination of the matrix applied to the individual vectors in that combination. But wait a second, all of these vectors u1 cap through un cap are eigenvectors. And so consequently, it's very easy to calculate the result. Now, take a look at this. Lambda 1 was assumed to be the largest in largest eigenvalue. Consequently, regardless of what alpha 1 is, alpha 1 times u1 cap will be magnified more so than any other term in that sum. Because again, lambda 2 is smaller than lambda 1. In fact, all of the other lambdas are smaller than lambda 1. Now, if we were to continue iterating, we would essentially continue to find a to the k applied to v naught cap. And applying the previous technique, this just results in alpha 1 times lambda 1 to the k times u1 cap plus the same for the balance of these eigenvectors in this basis. Let's suppose we divided this by that one largest eigenvalue raised to the power k. Well, so now on the left-hand side, we divide by lambda 1 to the power k. For the first term, it just cancels out. But for all subsequent terms, we now have alpha 2 u2 cap multiplied by the ratio lambda 2 over lambda 1 raised to the power k, and so on and so forth for every other term in this linear combination. Because lambda 1 is significantly larger than the second largest eigenvalue, it consequently follows that in the limit, as k becomes arbitrarily large, the ratios for every other coefficient go to 0. So all that would be left is alpha 1 u1 cap. Now, this assumes that we know what the first eigenvalue is, but what's important here is that, relatively speaking, all the other terms other than the first are quickly diminished in ratio with the first. Okay, here is a 5 by 5 positive definite matrix. It has a maximum eigenvalue lambda 1 equaling 6.147 and change, and there we see a corresponding normalized eigenvector for this eigenvalue. We're going to start with a randomly generated vector. Okay, so here's v naught cap. I just created a random vector and normalized it. Now, we're going to perform the following algorithm 10 times, starting with k equals 1. We're going to calculate vk equaling a applied to the previous normalized vector vk minus 1 cap. We're then going to print the magnitude of this vector. With our next step, we will normalize that vector to give us vk cap. And we're going to do this 10 times. So starting with v naught cap, we multiply v naught cap by a, and that gives us v1, which has a magnitude of 1.63 and change. And you will notice that 1.63 is not very close to the largest eigenvalue of 6.18 and change. However, we're now going to normalize v1 and then apply the matrix to that new normalized vector. Now, the matrix applied to that new normalized vector stretches it by a factor of 5.4 and change. And so it seems as if it's being stretched much closer, or v2 is much closer to that largest eigenvector. So then we normalize v2, and once again we apply the matrix. And let's print out the 2 norm. Notice it's getting very close to that largest eigenvalue. As we keep performing this, we see that with each subsequent step, A applied to the previous normalized vector produces a new vector that is approximately 1.647 times longer than the normalized vector. Basically, it seems that V7 is now significantly closer to being parallel with that eigenvector. Here's V8, V9, and V10. All right, so if we stop here and we normalize V10, we get that vector you see there. And if we compare it to the eigenvector corresponding to the largest eigenvalue, you'll notice that it's almost parallel. It's actually negated, so it's pointing in the other direction, but that's okay, because if U1 cap is an eigenvector, then any other scalar multiple, including -1 of U1 cap, other than, of course, 0, is also an eigenvector corresponding to lambda 1. So, with just 10 matrix vector multiplications followed by normalizations, we've actually come very, very close to the largest, or the eigenvector corresponding to the largest eigenvalue. And on top of that, we can calculate that largest eigenvalue simply by multiplying that normalized vector by A, and that will give us how much that approximation of the eigenvector is extended, which gives us an approximation of that eigenvector. That's nice. Thus, we started with a completely random vector. In fact, if you measured the angle between this randomly generated vector and the eigenspace of lambda 1, the angle is 76.5 degrees, so almost orthogonal. And yet, even though it appears that other coefficients were significantly larger, very quickly the coefficient of the maximum eigenvalue ended up dominating. So, yeah, after only 10 iterations, V10 is actually a very close approximation to the normalized eigenvector with the eigenvalue that we approximated in that process. Now note, there are better algorithms for finding the maximum eigenvalue and associated eigenvector, but this is nevertheless a very interesting algorithm because it works, and hopefully you can intuitively understand why it works. Also, it's reasonably straightforward. Compared to all the other algorithms of finding a maximum or all the eigenvectors, this one's actually quite simple. You just keep on multiplying and normalizing. That's something that you could have done a few weeks ago in this course. Now, an important thing is we introduced this discussion by describing positive definite and positive semi-definite matrices. What this did is it guaranteed us that the largest eigenvalue was positive. However, that's not guaranteeing that this will converge quickly. For example, if the second largest eigenvalue is close in magnitude to the first, we're going to see a serious slowdown in the rate of convergence. So this is really only useful if that largest eigenvalue is significantly larger than the other eigenvalues. Additionally, this algorithm can be used for finding the largest eigenvalue in magnitude if that largest eigenvalue in magnitude is negative, but then it requires additional considerations. For after all, A times the vector U will no longer be positive, but it will actually be pointing in the opposite direction. So after multiple iterations, it's going to bounce back and forth. Consequently, you have to take this into account when you consider convergence. It can even be used to find the largest magnitude eigenvalue if it's complex. But now we will be dealing with rotating eigenvectors. So yes, it applies, but it's not ideal. And you have to do a little bit more work. So this is an excellent algorithm if you have a positive definite or positive semi-definite matrix where you're guaranteed that all the eigenvalues are positive, and under the additional assumption that the largest eigenvalue is significantly larger than the second largest. Fortunately, in many applications of engineering, this actually happens to be the case. All right, so what? Why do we care only about finding the maximum eigenvalue and a corresponding normalized eigenvector? Well, quite easy. If lambda1 is significantly larger than the next largest eigenvalue, then generally a reasonable approximation to A times V, where V is an arbitrary vector in the vector space, is simply the projection of that vector onto that eigenvector times lambda1. For example, the matrix we saw previously, if we multiply it by the first canonical basis vector, gives us this result here. At the same time, if we calculate lambda1 times the projection of that first canonical basis vector onto that eigenvector, we get something that's actually not that bad an approximation. 1.278 is the fifth entry. 1.27 is the fifth entry of the actual matrix vector multiplication. The other values, similarly, are reasonably close. If I multiply A by the second canonical basis vector, I get this vector here, and lambda1 times the projection of that second canonical basis vector onto the eigenvector is once again this vector here. So again, we see now that that too is a reasonable approximation. The last entry of the actual multiplication is 1.37. In the approximation, it's 1.46. A little bit larger, but not unreasonable. Times a third canonical basis vector gives us that result. Projecting onto the third canonical basis vector onto the eigenvector multiplied by lambda1 gives us this result. And once again, it's not a bad approximation. Not necessarily great, but as a first estimate, it's not bad. We can do that with the fourth canonical basis vector and the fifth canonical basis vector. And in each case, we see that this is not a bad approximation. So in many situations in engineering, we're looking only for a reasonable approximation that can be quickly calculated. Well, multiplying a matrix by a vector generally requires many operations on the order of 2 times n squared operations. On the other hand, calculating the projection of V onto the first eigenvector and multiplying by lambda1 can be done with only 3n multiplications. So compare, say, 100 by 100 matrix. You have a choice between 20,000 operations or 300 operations. And if those 300 operations can get you a reasonably good approximation, then that's often good enough for certain applications. All right, following this topic, you now know what a positive definite or positive semi-definite matrix is. A symmetric matrix with all positive or non-negative eigenvalues. You know that given any matrix A, square or rectangular, both A times A transpose and A transpose times A must be positive semi-definite. And if A is square and invertible, then both are positive definite. You understand the power method allows us to approximate the largest eigenvalue of such a matrix, and as a bonus, we also get an approximation of the corresponding eigenvector. You're aware that the rate of convergence depends on how much larger the largest eigenvalue is in relation to the second largest eigenvalue, and you now know that if that first eigenvector is significantly larger than even the next largest eigenvalue, then this largest eigenvalue-eigenvector pair can actually be used to well approximate the behavior of the entire matrix at significantly reduced cost. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!